Okay, we're going to, as I mentioned, continue on. We're going to continue on here and wrap up chapter 2, I think, and exam 1 information. And I think that will be it for the evening. So we've been talking obviously about a few things here: electron configuration, orbital diagram, quantum numbers, obviously the periodic table and the relationship of all those things together. We hit a couple of these rules as we kind of went through electron configuration, but just again, a couple reminders of some of these. The off-ball principle is the idea that protons are added to the nucleus one at a time, and that's sort of how electrons are added to the atom, basically one at a time. As we were doing with electron configuration, again, they're always added lowest energy and kind of move their way up. As we saw, we don't obviously have to fill out any particular subshell or fill completely, but we just go until all the electrons are basically placed in there. And obviously, we have a specific order at which these go in when we have more than one electron present. And that's based on, again, how far sort of those orbitals penetrate towards the nucleus. And really, again, the major one in most electron configuration, as we talked about there, is sort of the S's before the D's in terms of the order at which you do that. Sometimes you will see people write electron configuration kind of in order, if you will, like, just all the ones together, the twos together, the threes together, and then maybe the fours. And sometimes you will see that, especially if you kind of look online and stuff like that. You should not do it that way. And it's not necessarily wrong to do it that way, but it is written in terms of energy and the energy after electrons are already in the atom. The way we write electron configuration, and pretty much every chemistry class that you take writes electron configuration, is they write it based on filling order. And that's that little chart that we made earlier. That is the order at which you should write electron configuration in this class. And pretty much most chemistry classes that you take, that is the way that you should write it. I only took one chemistry class my whole life that actually we wrote it the other way, but it was a more advanced sort of chemistry class. And it was based on energy rather than filling order. So again, you might see it if you look around in some places, see it written like that. And again, that's based on energy rather than how the electrons go into the atom. We talked about Hund's rule, where again, the sort of maximum number of unpaired electrons that is allowed by Pauli's exclusion rule. And again, to maximize that parallel spin, especially when we get into a degenerate sort of orbital. Degenerate means same energy. So like our p orbitals that we came across, again, to maximize that parallel spin before we go back again and kind of pair them up. And obviously we wrote our orbital diagrams and drew our orbital diagrams here. And again, arrows and boxes or lines to represent it. We talked about valence electrons as well there as we were doing electron configuration. But once again, valence electrons are the outermost energy electrons. So once again, here, if we look at this electron configuration of 1s2, 2s2, 2p6, that's a total of 10. That is neon's electron configuration. And neon's electron configuration, these here are on the highest energy level, and those would be our valence electrons, and that's going to be 8 right there. Yeah. And neon's actually in, as we just talked about, group 8 on the periodic table. So a really quick way that you can figure out the number of valence electrons for elements is that the number of valence electrons equals the group number on the periodic table. So if you want to write off the electron configuration, you can. But a much easier way is just to look on the group number. So for example, if we looked at sodium, which we also looked at, I think earlier, 1s2, 2s2, 2p6, 3s1. Once again, this being its valence electron, and there would be one. Sodium is group number 1 on the periodic table, so it will match the group number. So everybody in group 1 will have 1, everybody in 2, 2, 3, 4, 5, 6, 7, 8. The one exception in group 8 is helium. Yeah. Helium is in group 8, but helium has how many total electrons? Only has 2, so it can't have 8, right? So it only has 2 total. So even though helium, again, is part of group 8, it only has 2 electrons, and both are valence electrons in that particular case. That's also, as we'll talk about with bonding, why hydrogen only needs to get to helium to be happy, because it has just 1 more electron there, and that's the noble gas that comes after it. Everybody else in group 8 will have obviously 8 valence electrons in there. We also did fluorine, which was 1s2, 2s2, 2p5. Here are the 7 valence electrons in fluorine. So you can look at a periodic table and you can count the number of valence electrons, which equals the group number. And again, basically everybody in group 1 has 1, 2, 3, 4, 5, 6, 7, and 8. Now, what about our transition metals? Our transition metals in terms of valence electrons, well, you could just go by the regular numbering to figure that out. So the regular number means you just roll from 1, as you can see here, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And this would be 13, 14, 15, 16, 17, and 18. So for valence electrons in terms of transition metals, it actually equals those group numbers as well. So something like iron has 8 valence electrons. Something like zinc has 12 valence electrons. If you're counting something that's a transition metal, so you can just use that numbering for valence electrons for our transition metals. Any questions on that there? All right, let's see here. So we'll come back to that. I think we've done enough electron configuration, so we'll kind of skip that there. But I did want to now talk, speaking of transition metals, I did want to talk about electron configuration for transition metals. So for our transition metals, they are a little bit different in certain cases, and they're also a little bit different in terms of what happens when they do gain a charge in terms of electron configuration. First off, our transition metals are pretty much where the d orbitals are on the d subshell. So transition metals have incompletely filled d subshells, or they give rise to cations that have incompletely filled d subshells. Now, if you were to follow the electron configuration with that little chart that we used, and you were to write the electron configuration for certain transition metals, there are certain ones that really do not follow that sort of order, and has been found experimentally to be more stable in a different sort of configuration. So the 2 notable ones is chromium and copper. Chromium being number 24, copper being number 29. If you follow the electron configuration, that little chart that we had before, you would have 1s2, 2s2, 2p6, 3s2, 3p6. Remember that our 4s comes next, 4s2, 3d4. And if you did that for copper, it'd be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d9. Now, the exception actually comes at the end here, and it is this part of the configuration. And it's been found experimentally that actually copper and chromium are more stable with 1 extra electron up in the d orbital and 1 less electron in the s orbital. By the way, up through here on the configuration, that is 18. That is argon, as we talked about, yeah? So as you can see on the bottom there, for chromium, it is argon 4s1, 3d5. What that essentially does is it puts an unpaired electron in all the d orbitals, sort of maximizes the parallel spin there. And for copper, it is argon, same sort of deal, 4s1, 3d10. Again, 1 extra electron in the d orbital and 1 less electron in the s. How can that happen? Well, that can happen quite easily because if you look at where the 4s orbitals are and then our 3d orbitals, they're actually, in terms of energy, very close in energy. So it doesn't take a lot for an electron to sort of pop up there into the d orbital, not a lot of energy for it to do so, and it's able to do so relatively easily. As we will also talk about here in just a second, what actually happens once you start filling the d orbitals is there's actually a switch in the energy of these orbitals. And what ends up happening once you start populating the d orbitals is the 4s orbital actually ends up being higher in energy than, say, the 3d orbital. And that's what happens once you start sort of putting electrons into the d orbitals. You get this switch, which is also what I was just talking about a second ago, why sometimes people will write electron configuration after the electrons are in there based on energy, because based on energy, the 3d is actually less than the 4s, but based on filling order, it's opposite in the way that we should do it. So those two exceptions you definitely should know. If you look on the periodic table where chromium and copper are sitting, and if you go kind of down from there, each of them, and kind of come in, there's a lot of exceptions in that area. Things like silver is an exception. Things like PD is an exception. There are certain ones in the center there of the transition metal region that, for example, have all their electrons have gone up to the D and none in the S. So there's quite a number of exceptions to the normal sort of electron configuration. And if we take a look at some of those, here are some of the ones that we would expect. And here are the ones that are found experimentally for those guys. And as you can see, this is our chromium and copper with the extra electron up here. You can see when you get to something like PD, it's basically sent up both electrons and actually has no electrons anymore there as well. Again, silver is an exception as well. So kind of if you find chromium and copper on the periodic table, come down and kind of come in, there's a lot of sort of exceptions that occur. And it's really because these orbitals are really close to each other, so they can kind of shift electrons a little bit. It's not so energy impossible for that to happen. And you get some of these other configurations that are unusual. I'm going to say for us, you will be responsible for chromium copper. You should be aware that the other ones, obviously, in that area do have some exceptions. But for an exam or test, you can, for everybody else, just follow the order that we talked about earlier. And even though technically it may not be correct, we'll call it okay for our class. But you do need to know the chromium and copper exception. And again, everybody else you kind of write normally based on the configuration. Any questions on that there? Now, let's talk a little bit about that. So for example, let's talk about iron's configuration here. So why don't you write the electron configuration for iron, which is 26. Why don't you also do nickel, which is 28. Why don't you write the electron configuration? Okay, so let's take a look. We'll start here. Once again, we're going to start up on top. So we're going to go 1s2. We will then zigzag back there to 2s2. We'll come over here to p6, then to 3s, right? 2. Again, if we count up the top numbers there, we got 2, 4, 10, 12. So we got to keep going. We will then come to 3p next. And off to 4s after that. And now we're going to go to our 3d here. And that's going to give us 3d6 in this case. Once again, if we want to shorthand it, up through here is argon's configuration, and I'll be 4s2 3d6. Any questions on that? By the way, maybe you just saw me do it a second ago. It took like a second to recreate that. Yes, very easily on the page. So make sure you know how to do that, and it'll help you get obviously the right order and stuff like that. Here for nickel, we're pretty much just a couple down the road. So I'm just going to cheat a little bit there and borrow argon. and I know 4s2 there. So that's going to give me 18, and 2 more is 20. And obviously now I need to get to 28, and that's going to take me to my D, and that's going to give me 3D8 in this case. Yeah. Any questions on either of those configurations? So when we talk about transition metals and when they become ions, and because they are metals, they will lose electrons and become positively charged. They actually kind of go through a little bit different process than what we call kind of our representative metals, which are things in group 1, group 2, or group 3. Like we did sodium previously, we did aluminum. These guys, when they lose electrons, will actually end up back at the noble gas that comes right before them, as we saw earlier today. So when they lose electrons, they will back up. Transition metals are a little bit different in terms of how they lose electrons. And it has to do with what we were just looking at a second ago, that although in terms of energy, the 4s is lower than the 3d, once, as I mentioned, we start putting electrons in there, we will get this switch in energy. And again, that 4s will be higher than our 3d. And that's important because pretty much when things lose electrons, they will lose the highest energy electrons first. And because this switch occurs when transition metals lose electrons, so when transition metals lose electrons, they will always lose those s electrons first. Now, if they need to, after they lose the s electrons, which in most cases are 2, and they need to maybe lose 3, they have like a +3 charge or maybe a +4 charge, then they would go to the next highest electrons, which is now into the d. So that's why transition metals, when you look, have like 3, 4, 5, 6, 7, 8, 9, 10, all the way up there number of valence electrons, because they do in certain cases have those d electrons that they can transition. The other difference is typically a transition metal will not end up at a noble gas, because in certain cases that would require a lot of electrons to be lost, and he's like a +14 sort of charge, or something like that, which is not going to really ever happen. So they typically will not end up back at transition metals, but they always will lose those s's first. So that goes through all transition metals. When they gain a charge, they will lose those s electrons. So for example, if we take a look at iron, and iron with a +2 charge would have, instead of 26 electrons, because as a positive charge is lost 2 electrons, it will actually have 24 electrons. So what's going to happen is, if we look at the electron configuration here for iron with no charge, it will need to lose 2 electrons. And again, the 2 electrons it's going to lose is right there, those 2. So it will lose these 2 electrons, and the configuration here would be argon 3d6. So again, they will lose those 2 electrons. Now, what happens if I had iron with a +3 charge? That means that that guy actually will have 23 electrons. We already saw a second ago that I will have to take out 2 electrons from the s, but I still need to lose 1 more electron, and that will come from the d. We will knock out an electron there, and it will end up at argon 3d5. So transition metals are a little bit different in terms of how they lose electrons. Again, always going to ditch the s electrons first, and then if necessary, they will then go in and get rid of any d electrons until they've lost basically as many electrons as they need. Any questions on that there? So why don't you write the electron configuration for Mn2 plus and nickel with a 4 plus charge? What should the electron configurations be? Mn with no charge is 25 on the periodic table, and nickel, as we just did a second ago, is no charge, so that's 25. So again, argon, we have a 4s2 and a 3d5 action happening. So with a +2 charge, that means this guy should have 23 electrons. So it does need to lose 2 electrons. And once again, since it is a transition metal, it will lose those electrons first, and that's 2 electrons. That means our Mn with a +2 charge should be argon 3d5. Any questions on that one there? Looking at nickel with no charge like we did a second ago, that's going to be argon 4s2 and 1, 2, 3, 4. Actually, 3d8 we'll go with. Here with a +4 charge means it will end up with 24 electrons, as it lost 4 electrons. Once again, the first ones going out are going to be our 2s orbital electrons. We still have to lose 2 more, and those 2 are going to then come out of our D, which is our next sort of highest at that point. And that's going to leave us a nickel that has an electron configuration of argon. I'll go 3d6 on that case. Yeah. Any questions on that? So again, as you can see, transition metal is a little bit different in terms of what happens when they do gain a charge, and it always should be positive because they are metals. Again, you always want to take the S's and then the D's. Any questions on electron configuration of transition metals? And obviously, as you can see here, it does not get back to a noble gas configuration or anything like that. All right, so that is that. Now, I did also want to talk about the periodic table and electron configuration. Now, when you look at the periodic table, the first 2 groups are what are sometimes referred to as the s block. And s orbitals could hold 2 electrons. That's like 1 and 2, right? If you go from 3 to 8, that is what is known as the p block. And p subshell could hold 6 electrons. That is 1, 2, 3, 4, 5, and 6. The transition metal here, as we talked about just a second ago, that is our D block, right? And that is 10 electrons in the subshell. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And lastly, our 2 rows on the bottom here are lanthanide and actinides. Those are what are referred to as the F block there. F has 14, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. So if you know what you're doing, you can actually count off electron configuration from the periodic table. You remember that our N numbers, our principal quantum numbers, go from 1 to 7, yes? There are 1, 2, 3, 4, 5, 6, and 7. Those are your N numbers, yeah? So the period numbers are actually your principal quantum number when you look on the periodic table. So let's just say, for example, here, some of my markings, I don't know. Actually, here we go. I'll just take a fresh one here. Let's say we wanted to go to sodium, which is right there that we just did previously, I think. Go right there. So if we wanted to end up at sodium, we would start like this, starting here at period 1. 1s2 would come to there, 1s2. Right here would be 2s2. This is still period 2 in the p block, so that's going to be 2p6 and 3s1 right there, yeah. So you could basically count off the electron configuration if you want to do it that way. We did maybe, we could look at chlorine, right, if we want to go further. So we would do the same thing there. We would start with our 1s2, our 2s2, our 2p6. We then could go, in this case, now all the way across here, that is 3s2. Now we're going to come over here, and this is 3p1, 2, 3, 4, and 5. So that would be 3p5. So if you know what you're doing, you could actually count off the electron configuration along the way. Now, let's just say we want to do iron, which we also just did, which is right about there. And again, I'll just keep what's up there and kind of erase this part of it here. So starting again at top there, 1s2 to helium, 2s2 to beryllium, 2p6 all the way to neon, 3s2 to magnesium. Now we would go all the way across here. This would be 3p6. We're now on period number 4, 4s2 there. And now this right here is D. Which D is this? D start at what energy level? It is 3. So that's actually 3D, even though it's on number 4. So that's actually 3D. This would be, by the way, 4D, 5D, 6D. So the D's are 1 behind the period number. So that would be 3D, 1, 2, 3, 4, 5, and 6. Yeah, 3D6 all the way across there. So it's very important to remember that it does get a little bit 1 behind as you get to transition metal. Also, if we get down here, right, this is the F's down here, right? And F starts at what energy level? 4th. That's 4F. That is 5F. Those really go over here, right? That means the 4F really would be right about there, which is 2 behind the period number. And the 5F would be also 2 behind the period number. So there are places that if you want to just sort of count off the electron configuration on the periodic table, you do have to be really careful, especially in the transition metal region, that you don't give the wrong numbers and stuff like that. Definitely, if you kind of take the chart thing that we've been using, you should always get the right one. If you want to test yourself or double check yourself here, you can use the periodic table to count off electron configuration. Any questions on periodic table and electron configuration? Yeah. All right, that we introduced and did. So one more time there. All right, so the last thing we're going to talk about, those are the words we want to hear. The last thing we're going to talk about here in this chapter, my seat as well, as long as your seat as well, those are the words I want to hear. We're going to talk about periodic trends, and obviously we did an experiment the other day that kind of had periodic trends involved. So we're going to talk about these several different periodic trends, and a couple more are going to add to it, and it should hopefully explain sort of what we sort of saw the other day when we did the experiment, and just in general periodic trends. So we're going to talk about ionization energy. We'll talk about electron affinity, atomic radius. We will also talk about effective nuclear charge. And that is what's sometimes referred to as Z effective. And that's a Z. And we'll talk about electronegativity as well. And electronegativity is actually in chapter 3. It is the only thing from chapter 3 that you'll need to know for the first exam. When we get to chapter 3, we'll talk a lot more about electronegativity. So in terms of electronegativity, it's in the context of periodic trends. So what you'll need to know for the first exam is sort of what it is. And obviously it's periodic trend. When we get to chapter 3, you'll need to know a bunch more about it in terms of bonding, but that will be for exam 2 material. So that's a little bit of chapter 3 that will sort of be on this first exam. So let's talk about each of these. Let's actually start with effective nuclear charge, I think, is where I want to start. I did leave a spot there. It's good. So let's talk about Z effective, which is, again, our effective nuclear charge. And let's just take a kind of simple sort of example really to illustrate what it is sort of talking about. So let's say, for example, we had lithium, right? And lithium here has an electron configuration 1s2, 2s1. It has 3 total electrons. Lithium is group number 1 on the periodic table, which means it has 1 valence electron, right? These are its core electrons. And that would be, again, its 1 valence electron. So when we look at lithium, because it is atomic number 3, it is basically sitting with a +3 nucleus, right? And it's got 3 protons in there. It's got some neutrons in there, but they have no charge. But it's really the 3 protons that are sitting in the nucleus that has a +3 charge. Now, we have 2 electrons that are the core electrons in this case, which are really closer to the nucleus, right? So if we were to draw kind of those first energy level electrons, and again, I'm just going to kind of draw them like they're right there sitting, and we know where they're at. And then obviously on the second energy level here, we have one more electron, which is our valence electron. And again, I'll just draw like I know where it's at, like sort of there, right? Now, what happens in this situation is a couple of things. And the first thing that we should talk about, which I think we might have, but in case we have not, obviously the attracted force between positive and negative, there is an attraction force between that. That is what is known as electrostatic attraction. Opposites attract. And really the sort of strength of that opposites attract, the positive negative attraction, does increase with increased charge. So something like +3 and -3 will actually be held a lot tighter than something like +1, -1 that comes together. So that relationship is also really important for what happens when we look at electrons, say, involved here in our simple example of lithium. We have these core electrons, which are closest to the nucleus, and pretty much those guys are feeling the full brunt of that +3 charge, right? They're like up front and center. Not sure exactly where they're at, but they're moving around pretty close to the nucleus. They're going to feel the full brunt of that +3 charge, which means those electrons are really going to be attracted to the nucleus pretty strongly, right? Because that's why they're core electrons. They are just going to feel that full force of the +3 charge. Now, when we talk about our valence electron up here, there is something different in terms of what he is feeling than, say, those core electrons. And it's actually the core electrons that, frankly, get in the way. And they're kind of in front of, if you want to think about it that way, this valence electron. And they're sort of blocking the valence electron from feeling the full brunt of that +3 charge. It's kind of like in the movies years ago, you could pick your own seat, right? You get there early, you get the nice center seat, right? And like right before, like, the movie starts, somebody sits in front of you with a giant hat, right? They just shielded half of the screen. And this valence electron actually feels what is referred to as shielding as well. And it feels shielding from these lower energy level electrons, and it's shielded from the full brunt of the positive charge that's in the nucleus. The result of that is, instead of that valence electron feeling a +3 attraction, which is a relatively strong attraction, it is going to feel something like this. You could actually calculate it. You could take the +3 charge of the nucleus and count up how many electrons are shielding that guy, which in this case is 2. And now that valence electron, instead of feeling a +3 sort of attraction, it is actually only feeling a +1 attraction to the nucleus as a result of shielding that's happening in this particular case. Electrons are shielded by electrons in lower energy levels. Electrons in the same energy levels don't shield each other, but ones in lower energy levels will shield ones further. What does that mean? That means that if I wanted to rip off, for example, the valence electron versus the core electron, which one should be easier to remove? Should be the valence electron, because it's only feeling like a +1 pull on it, right? While those core electrons are feeling this +3 pull on it. It's going to keep those electrons tight and not going to be allowed to remove. As we'll talk about and probably have mentioned already, that is why valence electrons are the ones involved in bonding. They're not held as tightly because of this effective nuclear charge, which allows them to be kind of removed a little bit easier. Any questions on that? Now, in terms of the periodic table, if you look at the periodic table, effective nuclear charge increases as you go up and to the right and decreases as you go down. And if you just think about the periodic table, as you go to the right on the periodic table, the atomic number increases, right? And if the atomic number increases, the number of protons increase, which means just baseline nucleus you have a much larger positive charge than you do with somebody to the left on the periodic table. They have less protons and less positive charge pulling on those protons or electrons. Any questions on that there? So in addition, another really important sort of periodic trend is ionization energy. And ionization energy is the energy that is required to remove an electron from the gas phase. So when we lose an electron, things become positively charged. And when we talk about ionization energy, that is basically the formation of cations. So the ionization energy is really what happens when somebody loses an electron. The result of that is they will become positively charged and form a cation. We could represent that with this equation. We have X has no charge like a metal. The metal becomes positive charge, electron on the product side here. And that's like is being lost, is what's being represented in that case. Now, electrons actually do come off one at a time. So things do not just dump out like 3 electrons at a time or 2 electrons at a time. They actually come off in sort of a stepwise fashion. So if we look at magnesium, for example, down here, the first thing that would happen is this magnesium with no charge would dump off an electron. And the energy required to do that is what is referred to as the first ionization energy. So the first ionization energy is the energy required to remove the very first electron in like a metal. Then what will happen is that magnesium that has a +1 charge will drop off a second electron and now become +2 charge. That is what is referred to as the second ionization energy, the energy required to remove the second electron. Then maybe magnesium drops one more electron, becomes a +3 charge. That is the third ionization, third ionization energy in this particular case. Now, what we see is the first amount of energy required to remove the first electron, about 735 kilojoules per mole. To pop off the second electron, is it easier or harder to do? Does it take more or less energy to pop off the second electron? It takes more. It's a lot harder to do, about twice as hard, if you want to think about it that way. It takes twice the amount of energy to do that. That is because when somebody loses an electron, so if you have a neutral atom and it becomes a cation that's positively charged, does the thing get larger or smaller when it becomes positively charged? Becomes smaller, right? It loses an electron cloud and it becomes smaller, right? So the cation versus the neutral atom is actually smaller in size. That means even your outer electrons have now just moved closer to the nucleus, right? They're not as far away, and that's going to hold them tighter. And as you can see there, the result of that is it takes a lot more energy to do that. Third one takes even more energy, right? We're now about 10 times the amount of energy needed to do the first electron. We're at 7,700 for magnesium. So in terms of first ionization energy to second to third, the amount of energy increases every time you try to take off an electron because you're just moving the thing smaller and smaller. Electrons are getting closer and closer to the nucleus and going to be held tighter in that case. The general trend in ionization energy, first ionization energy, is it increases as you go up and to the right, decreases as you go down and to the left on the periodic table. Now, if we were to write magnesium's electron configuration, a little 1s2 action, 2s2, 2p6, 3s2. Magnesium's got how many valence electrons? Magnesium's group number 2, which means it has those 2 valence electrons right there, yeah? Where do we see the giant jump in energy? After the first one, second one, or the third one? Between these two, yeah? It goes up like 7-fold, 6-fold almost at that point. And that is because after we get rid of this one and this one, what is left in terms of electrons? No more valence electrons. These are all core electrons, yeah? Good luck trying to remove that. Doesn't really happen. That's why magnesium typically has a +2 charge. That's as far back as you could go because you're not going to be able to, energy-wise, be efficiently able to rip off that core electron. So even though it's possible to happen, energy-wise, it's not favorable to happen. And that's why certain things have fixed charges, like magnesium, or really anybody in group 2, for example, has a +2 charge because of that. And just why anybody in group 1 has a +1 charge because of that as well. Because energy wise, after you get rid of that first valence electron for somebody from group 1, you're into the core electrons, which again makes it a lot harder to do. Any questions on that there? So here's a table, and you have a similar one in your book, which is probably that table right there. And again, you can see here, there's our magnesium +1, +2, no +3. We have our sodium. It goes from 495 for the first electron and then jumps up to 4,500 tenfold times. Again, because at that point, you've now jumped into the core electrons. There's our aluminum. First one, not too bad. Second one gets harder. Third one gets harder. Super hard if you want to try to pull off that fourth one, right? It's not going to, again, typically happen. So, in general, what we see is as you continue to remove electrons, it gets harder and harder to remove those electrons because, again, everything shrinks down. Outer electrons now move closer to the nucleus. They're held tighter, takes more energy to do that. And you really, for most case, will not be able to pop off those sort of valence electrons as well. We also see when we get over here, these guys are kind of like non-metal action, yeah? Their first ionization energy is quite large. And again, they typically don't lose electrons, right? They are typically, as we'll talk about, ones that gain them. So again, we see that sort of transition. And as we go again across period 3 there, we see an increase in the first ionization energy. So in general, we go across the period, the ionization energy increases, and that's because, again, electrons are added to the same principal quantum number. They don't get shielded, and electrons in the same one are going to be stronger held as you go to the right. So in general, as we go down a group, the first ionization energy decreases. And what happens as we go down a group, the electrons on average are further away from the nucleus, and they're also larger to accommodate that. So if you go left and down on the periodic table, you're hitting some pretty big atomic numbers, which means they have an equal number of electrons. And remember that as you put those electrons into those orbitals get bigger, right, and bigger to accommodate those electrons. So now those outer electrons are finding themselves really, really further away from the nucleus and not going to be held as tightly and can be able to be removed a lot easier. Here's just our general trend across a group for ionization energy. And it's not perfectly linear, and that's because, again, we have electron repulsions. They don't want to be near each other, so there's a little bit of some variety in terms of the ionization energy. It doesn't linearly sort of increase as you go one way or decrease as you go the other. All right, so let's try this one here. Which atom should require more energy to remove an electron? Is it sodium or chlorine? Which one should require more energy to remove? So sodium and chlorine are in the same period on the periodic table, yeah. Chlorine is further to the right, which means has a slower or higher ionization energy. Should have a higher ionization energy. Again, it will have more protons, bigger effective nuclear charge, going to take those outer electrons closer to the nucleus, going to have a much higher ionization energy as well. Which one should have more energy to remove an electron? Lithium or cesium? They are in the same group, these two. So which one should require more energy to remove? Ionization energy increases in a group which way? Increases as you go down a group. Again, cesium has a lot more protons and electrons, which means those outer electrons are further away. Lithium has only 3, which means those outer electrons are relatively close to the nucleus. So it's going to hold it a lot tighter, which means it's going to take a lot more energy. And I think I said it backwards. I'm sorry. The ionization energy decreases as you go down. So ionization energy decreases as you go down. So it's a lot easier to remove the electrons in that case. So ionization energy decreases that way, increases that way on the periodic table. So I think I misspoke there. So the one that should take the most is lithium in this case, not cesium, because it's further up in the group on the periodic table. Which one should have a larger second ionization energy, lithium or beryllium? So this is second ionization energy, which basically means we're talking about what electron coming off. Second one. So let's take a look at lithium, which is 3, 1s2, 2s1. And we're looking at beryllium, which is right next door on the periodic table there, which should be 1s2, 2s2. Yeah. So which one should have the higher second ionization energy, you think? It should be lithium, I think I heard. And it is because lithium has how many valence electrons? 1, which means the second one we would now be into the core electrons, right? And that's definitely going to be a lot higher than beryllium that has how many valence electrons? 2. So you still be popping off valence electrons at that point, which should be a lot less and stuff. So lithium should have the higher second ionization energy in this particular case. Any questions on that there? Let's talk about another trend that's important, which is electron affinity. And electron affinity is different than electronegativity that we'll talk about here in a second. But electron affinity is actually the energy change that occurs when somebody gains an electron. So when somebody gains an electron, it's the energy change that occurs. And if you have an affinity for something, you could just think about it like you like something, right? If you have an affinity for it. Um, so that's what we see here. We have somebody gaining an electron becoming negatively charged. In general, electron affinity increases as you go up to the right and decreases as you go down to the left. And since this is about somebody gaining electrons, we usually associate electron affinity with anion formation, which is our negatively charged ions. The general trend is, like I said, there increases as you go to the right, decreases as you go to the left. It's not a perfect sort of trend in terms of the energy. If you looked at group 7, which is your halogens, what you would see is the energy would kind of increase, then it'll kind of come back down at the top. So it's not like a perfect sort of trend, but the overall trend is it increases as you go to the right, decreases as you go down. Now, another important aspect of periodic trend is atomic radius. And when we go to the right, we do see the atomic radius get smaller. And that again is because as we go to the right, we have a greater buildup of protons, which means our effective nuclear charge is going to be bigger. It's going to bring those outer electrons in closer and give the overall size of the atom to be smaller, as opposed to the left, where we have the electrons further away from the nucleus and it can't feel, it's shielded a lot more as well. It's not going to feel as much of that positive charge, so it's not going to be drawn in as tightly here as you go to the left. So when we look at it, the general trend here is as we go to the right on the periodic table, size gets smaller. And as we go down, it gets larger as well. We talked about the neutral atom, right? To the cation is smaller. What about the neutral atom to the anion. Is the anion larger or smaller than the neutron? Actually should be a little bit larger because it's now gained electrons, right? So the anion's electron cloud actually increases as it gains the electrons, so it becomes larger as you go that way. Question on that there. One last sort of trend that we want to add to sort of our list is electronegativity. And electronegativity is the ability of an atom to bring electrons towards itself. And on the periodic table, electronegativity increases as you go up and to the right, decreases as you go down. Our friend fluorine is the most electronegative element you could have. So fluorine is the most electronegative element that you could have in this case. So all these trends, when you kind of take them together, sort of shows us what we typically see when we look at metals, say, versus non-metals. So find a better place to do this here. Maybe I'll just do it here. So if we take a look at a periodic table and we think about all of our sort of trends that we talked about, we have the effective nuclear charge increasing as you go this way, decreasing as you go this way. We have our ionization energy increasing as you go this way, decreasing as you go down. We have our electron affinity increasing as you go up and to the right, decreasing as you go down. We have our electronegativity increasing as you go up and to the right, obviously with fluorine being the most, and decreasing as you go down. And we have atomic size decreasing as you go up and to the right and increasing as you go down. So all of these trends basically work together for what we see happen. If we think about the sort of upper right of the periodic table in this area, we have things that have a strong or high effective nuclear charge. So even the outer electrons are feeling a pretty good pull towards the nucleus. Because of that, we have a much smaller size of the overall atom. And because of that, we have a very high ionization energy, which means they typically do not like to lose electrons. They have a high electron affinity, which means they typically rather gain electrons. And they have a very high electron negativity, which means in addition to gaining electrons, they also like to bring electrons towards themselves. All of those trends together is why when we look at nonmetals, which are in the upper right of the periodic table, they typically like to gain electrons and not lose electrons and become anions and negatively charged. That is opposite if we kind of go bottom left of the periodic table, where we have a lower effective nuclear charge. So those outer electrons aren't going to be pulled in as tight. That's going to result in a larger size for the atom, which means that you do not need a lot of energy to release the electrons or remove them. And they have a very low electron affinity, which means they're not in the neighborhood of I want to accept electrons. They're not looking to gain electrons. And they also have a very low electronegativity, which means that they're not looking to bring any electrons towards themselves. So that all works really well for what we know down here, which are metals typically will lose electrons and become cations, which are positively charged in this case, right? That is why, as we'll talk about when we talk about bonding, when you take a metal and a non-metal together to make an ionic compound, the metal has all the periodic trends that say, take my electrons, please. and the nonmetal has all the periodic trends that say we would like your electrons, so thanks. And that is why in an ionic compound we get a transfer of electrons from the metal to the nonmetal and makes a cation and an anion. That is also why we'll talk about when we talk about bonding that we have covalent bonding, which is sharing of electrons, and that is when you get a couple of nonmetals together. And if you get a couple of nonmetals together, they're in the same spot on the periodic table, which means they both have the same sort of periodic trends, which means neither one of them wants to lose electrons or give up their electrons. So the best they could do in that situation is share electrons. And that's why we get covalent bonding when we have two nonmetals come together, rather than a transfer of electrons that occur when we get to things like a metal and nonmetal that have very different periodic trends. Any questions on that? I think that's right. I think I said that right. So obviously you do need to know the periodic trends. You need to know what they are. You know their general trend on the periodic table. Any questions on that? That also correlates to what we saw in our experiment, right? When we looked at the halogens, reactivity increased which way in group 7? When you went up. Most reactive was upper right of the periodic table. That's our most reactive nonmetal. Perhaps, hypothetically speaking, when you looked at your two metals in that experiment, I think it was magnesium and calcium, you probably saw reactivity increase as you went down the group, right? Most reactive metals, bottom left of the periodic table, again, for those reasons. Bottom left of the periodic table, as you go down a group, they're like, just take my electrons. You don't have to do a lot of convincing. That's going to make them really, really reactive, right? Because they're able to give away their electrons really easily. As opposed to on the upper right, as you go up and reactivity increases, they also have periodic trends where they're going to try to rip off and take electrons from somebody that gets near them, which makes them quite reactive as well, because they're going to try to pull electrons towards themselves so that they can gain them. And that's why we see the most reactivity on those kind of opposite ends of the periodic table. Top right there for our nonmetals, bottom left there for our metals. Any questions on that there? All right. So that is that there. That is that. A couple of final ones here. Let's see. Which should be larger, sodium or chlorine? Which atom is larger? It is. Again, sodium, chlorine in the same period on the periodic table. Sodium is further to the left, right? Which means it has a smaller effective nuclear charge. That's not going to pull the electrons in as tight as chlorine will pull those electrons in. So it should be sodium in this case, yeah. Which one should be the larger atom, lithium or cesium? It is going to be cesium. Again, effective nuclear charge increases as you go up. Lithium with its 3 electrons going to have a much stronger pull on those 3 electrons than obviously cesium that has a lot more than 3 electrons. So cesium will be a larger atom. Which one is larger, the hydrogen 1s orbital or the lithium 1s orbital, and which one is lower in energy? The hydrogen 1s orbital or the lithium 1s orbital? Take a moment and think about each of those. To look, let's just draw some pictures and see what we got going on. Hydrogen's got 1 proton, so that's a +1 charge and 1 electron. Lithium, as we saw earlier, has a +3 charge and a few electrons hanging out, right? So we're talking about the 1s orbital, which would be these guys here, right? So which one should feel a stronger attraction to the nucleus? Hydrogen or lithium's? It would be lithium. Again, it's +3 versus +1. That's going to make the 1s orbital come on down closer, right? That is also going to move everybody in closer, which means the overall size should be smaller, right? That means our 1s electron here in our hydrogen won't feel as strong of a pull, so it'll keep a little further of a distance and should be larger. So hydrogen's 1s orbital here should be larger because it's not going to feel as strong of a pull towards that nucleus. By that same token, which one should then be lower in energy? Remember, lower in energy should be the one further or closer to the nucleus. Lower in energy is when you are It's a 50-50 chance when you are closer to the nucleus, right? So that's where the lowest energy orbitals are, closer to the nucleus. So which one got pulled closer to the nucleus? It is the lithium one because of that. So that would actually end up being closer to the nucleus because of that. Any question on either of those there? No? All right. Arrange these in order of increasing ionization energy. So if we just look at the placement on the periodic table, we got sulfur right above it. We got oxygen, and to the right, we have fluorine, right? So that's basically what it looks like on the periodic table. So ionization energy increases as you go this way and decreases as you go this way. So we want to do it in increasing order. So that would mean sulfur, oxygen, fluorine, like we got going on there, should be the increasing order. And atomic size, it gets smaller this way and larger this way, which means we're going from fluorine to oxygen and then to sulfur, which would then be the larger of all three of those guys. Any questions on that one there? Final thoughts? I feel like we did our final thoughts on this. All right. So again, here's a nice little guy. You do need to know where all those guys are located, obviously, as we talked about. Chapter 2. There we go. Any questions?